All right, on number 5, it's a combination circuit, meaning we don't just have series and parallel, we have some aspects of each. So if you're the positive charge, you're coming out of the gate and then you hit this R1 before, you have to make a decision to either go down pathway R2 or pathway R3. So R1 is in series to this parallel branch. It's basically all the charge has to go through this one, but not all the charge has to go down both of these branches. Some will go down R2 and some will go down R3. So resist the urge, sorry for the bell there, resist the urge to just say, oh, I got 3 resistors, I just add them all up the way it is. Instead, you have to kind of go through your equivalent resistance rules in order to solve that. So one way of doing this is to reduce R2 and R3 because those are in parallel to each other, get the equivalent resistance of that, and then add it to R1 to get your total. Once you know your total, then you can get your current, and then you can start using those values to decide, how much is going down each line. All right, so the math of that, this kind of equivalent resistance here, we'll just call it the equivalent resistance. It's not really the total resistance of the circuit, so we'll just call it equivalent. Equivalent meaning like, what is this acting like when it's set up this way? Well, that's acting like a 20 ohm and a 30 ohm in parallel. And you'd solve that by doing the inverse of the sum of the inverses. And so looking for common denominators, I could rewrite that as 1 over 3/60 plus 2/60, which would equal 1 over 5/60 or 60 over 5. And so your R equivalent for that part of the circuit is just 12 ohms of resistance. So this whole chunk of the circuit, it's really just like it's a 12 ohm resistor. If I redrew my circuit, I could draw R1 and then a 12 ohm resistor, and it's effectively the same exact thing as what I have up above. So if R1 is 10 ohms and this equivalent section here, it's coming from these up there, is acting as 12 ohm, that would put the total resistance to be 22 ohms of resistance. All right, from there you can use Ohm's law, V equals IR, and solve for that total current coming out of the battery. And that, if back in our drawing, that would be like the total amount coming out here, which is also going to be how much flows across this R1. We'll call it I1, but it's really the same as the I total. So once we get this I total, these two boxes are going to be identical because the amount coming out of the battery has to go across that R1. And it's also going to come back to the battery and be I total over here. But that's just kind of keeping track of that so far. We'll go back and solve for I2 and I3 later, but let's get this done first. So I have 6 volts equals I total times 22 ohms. Again, anytime you have 2 of the 3 things in Ohm's law, you can solve for the missing. So I take 6 divided by 22, and I get a total current of 0.27. Repeating, I'm just going to round it and say 0.27 amps. So since I know that this one, the total was 0.27 amps, that's how much is also going to be going across I1, so there's 0.27 amps flowing across there. And again, I have 2 of the 3 things. I can solve for now the voltage drop across that first resistor. So taking 10 times 0.27, I get a value of 2.7 volts. And if you notice down at the bottom, I have to drop 6 volts total. So my battery pack has 6 volts from the high side to the low side. And if I drop 2.7 just by going across that first bulb, I started at 6. Think of it like a hill analogy. I'm going to draw up here. You're starting at a height of 6, and then you just dropped in height a total of 2.7 um, as your delta, your change in height. So now I'm at a platform that's only 3.3 meters in the air, and to get down to 0, I'd have to change another 3.3 meters. The change here would be 3.3 in order to get myself down to a position of 0. So no matter which pathway I go down, whether it's the R2 branch or the R3 branch, I have to drop that voltage of 3.3 volts to get myself back down to 0, which is connected to the low side of the battery. So I drop 2.7 by going across R1, then I'll drop 3.3 whether I go down this channel or this channel. Remember, voltage is not the stuff flowing through the wire. It's a measure of energy difference per charge from one side to the other. So we have to kind of not mix up our current and voltage rules about like what's happening in series and parallel, but rather think of that as like you're dropping down, you're stepping down in voltage every time you go across these resistors, and you have to step down the total amount that's in your battery pack. So filling that in then, if you had 3.3 volts across each of these, no matter which branch you would go down, and you have the equivalent, you have the resistance of each of these lines, then you can solve for how much individual current is going to each of these sections. So I'm just going to take 3.3 divided by 20, and I get a value of, let me change this here. I get a value of 0.165 amps, and then I do the same thing, take 3.3 divided by 30, and I get 0.11. If you add those two numbers together, you get back to that 0.27. In this case, it works out to be like 0.275 because I've been rounding, but you notice that it gets back to that total that it was. It just split up in those two branches. So there is some rounding errors that are going to go in if we're just kind of like assuming that we cut off the 0.27 repeating. But on this worksheet and the things for the AP exam, that's not as important, that you express everything in fractional form. Rounding is acceptable to get yourself to a value. All right, number 6 and 7 don't show up on the same, they're on the next page, but I'll just kind of talking through it. The first thing they want is what is the equivalent resistance of all these parallel resistors hooked up in this way. How does that actually acting as a resistor? So we'll just use our 1 over rule for that and solve. So number 6 is to get the equivalent resistance, and that would just be 1 over, and then you just list each one. 1 over 6 plus 1 over 12 plus 1 over 36 plus 1 over 18. And it looks like they were nice to us and they had a common denominator in there of 36. So I have 6. Oops, I still need to do the, just a second here. I still need to do the 1 over. So this is the same thing as 1 over 636 plus 336 plus 136 plus 236. Adding up all those fractions, I'm getting 6, 7, 8, 9, 10, 11, 12. I'm getting 12 over 36, but then it's down in the denominator, so I'm going to flip that one more time. And I got 36 over 12. The equivalent resistance is 3 ohms. So all of those things are acting just like a 3 ohm resistor. And again, if you follow through that math, I did 1 over 12 over 36. And so you flip that fraction, you get 36 over 12, which is 3. So that is how you would solve number 6. To solve number 7, number 7 relies on that you have the voltage drop. So you see that the 12 volt side of the battery, and this would be considered like the 0 volt. If you want to rewrite that battery as like going from 12 over to 0 by the time you get around the circuit. No matter any of these pathways I go through, whether it's this one, this one, this one, or this one, I have to drop all 12 volts of potential difference by the time I go across those, or else I would have I'd still have potential left over. By the time I hit the bottom side of the circuit, anything that's connected to that 0 volt line, it's not connected to anything else, I would have to drop all the voltage that I had to begin with. So I have 12 volts. I'm going to drop 12 volts regardless. So I know that there's 12 volts of drop across this branch. Let me pick a different color here just to kind of show this easier. So I got 12 volts of drop across this, and I got 6 ohms of resistance, so that makes the math of that pretty easy. V equals IR. The 12 divided by 6 is going to give you a current of 2 amps flowing down that channel.